合作关系。产学研投融合创新服务的运维模式，助力科技信息的无障碍传播，加速信息的整合利用，推动科技人才在全球范围内的流动及合理化配置，促进学科交叉和产学研互动。未来，科研云致力于打造科研传播第一品牌。穿越时空的科研之云，拥抱科技进步的脉动，在科研的广阔天空中，每一颗星辰都闪耀着探索真理的光芒。科研云自2020年3月创办至今，目前已发展成为中国最大的科研科技传播平台，旨在为学术和产业界一线科研人员提供一个了解和交流国际前沿科技的新途径，希望能以最便捷高效的方式，密切连接平台订阅用户与学术界、产业界的专家学者，一起交流国际学术和产业界的研究进展，促进学科交叉和产学研互动衔接，引爆思维火花的碰撞。基于科研云科技学术平台的品牌优势，萃取海量学术视频信息，打造新型科技数据库和专家数据库，并承接国内国际品牌学术会议的宣传、直播、承办等业务，服务于政府的科技规划和政策实施，高科技企业的科技成果转化和技术咨询，高等院校和研究所的人才招聘和学科建设评估等项目，打造一站式科研服务平台，包括科研耗材、科研绘图、理论计算、材料测试、论文润色、仪器选型分析和销售、科研 AI 等科研服务，与国内外100余家顶尖院校、学术期刊、知名学会、投资机构建立深入合作关系。产学研投融合创新服务的运维模式，助力科技信息的无障碍传播，加速信息的整合利用，推动科技人才在全球范围内的流动及合理化配置，促进学科交叉和产学研互动。未来，科研云致力于打造科研传播第一品牌。穿越时空的科研之云，拥抱科技进步的脉动，在科研的广阔天空中，每一颗星辰都闪耀着探索真理的光芒。科研云自2020年3月创办至今，目前已发展成为中国最大的科研科技传播平台，旨在为学术和产业界一线科研人员提供一个了解和交流国际前沿科技的新途径，希望能以最便捷高效的方式，密切连接平台订阅用户与学术界、产业界的专家学者，一起交流国际学术和产业界的研究进展，促进学科交叉和产学研互动衔接，引爆思维火花的碰撞。基于科研云科技学术平台的品牌优势，萃取海量学术视频信息，打造新型科技数据库和专家数据库，并承接国内国际品牌学术会议的宣传、直播、承办等业务，服务于政府的科技规划和政策实施，高科技企业的科技成果转化和技术咨询，高等院校和研究所的人才招聘和学科建设评估等项目，打造一站式科研服务平台，包括科研耗材、科研绘图、理论计算、材料测试、论文润色、仪器选型分析和销售、科研 AI 等科研服务，与国内外100余家顶尖院校、学术期刊、知名学会、投资机构建立深入合作关系。产学研投融合创新服务的运维模式，助力科技信息的无障碍传播，加速信息的整合利用，推动科技人才在全球范围内的流动及合理化配置，促进学科交叉和产学研互动。 未来，科研云致力于打造科研传播第一品牌。穿越时空的科研之云，拥抱科技进步的脉动，在科研的广阔天空中，每一颗星辰都闪耀着探索真理的光芒。科研云自2020年3月创办至今，目前已发展成为中国最大的科研科技传播平台，旨在为学术和产业界一线科研人员提供一个了解和交流国际前沿科技的新途径，希望能以最便捷高效的方式，密切连接平台订阅用户与学术界、产业界的专家学者，一起交流国际学术和产业界的研究进展，促进学科交叉和产学研互动衔接，引爆思维火花的碰撞。基于科研云科技学术平台的品牌优势，萃取海量学术视频信息，打造新型科技数据库和专家数据库，并承接国内国际品牌学术会议的宣传、直播、承办等业务，服务于政府的科技规划和政策实施，高科技企业的科技成果转化和技术咨询，高等院校和研究所的人才招聘和学科建设评估等项目，打造一站式科研服务平台，包括科研耗材、科研绘图、理论计算、材料测试、论文润色、仪器选型分析和销售、科研 AI 等科研服务，与国内外100余家顶尖院校、学术期刊、知名学会、投资机构建立深入合作关系，产学研投融合创新服务的运维模式，助力科技信息的无障碍传播，加速信息的整合利用，推动科技人才在全球范围内的流动及合理化配置，促进学科交叉和产学研互动。未来，科研云致力于打造科研传播第一品牌。穿越时空的科研之云，拥抱科技进步的脉动，在科研的广阔天空中，每一颗星辰都闪耀着探索真理的光芒。科研云自2020年3月创办至今，目前已发展成为中国最大的科研科技传播平台，旨在为学术和产业界一线科研人员提供一个了解和交流国际前沿科技的新途径，希望能以最便捷高效的方式，密切连接平台订阅用户与学术界、产业界的专家学者，一起交流国际学术和产业界的研究进展，促进学科交叉和产学研互动衔接，引爆思维火花的碰撞。基于科研云科技学术平台的品牌优势，萃取海量学术视频信息，打造新型科技数据库和专家数据库，并承接国内国际品牌学术会议的宣传、直播、承办等业务，服务于政府的科技规划和政策实施，高科技企业的科技成果转化和技术咨询，高等院校和研究所的人才招聘和学科建设评估等项目，打造一站式科研服务平台，包括科研耗材、科研绘图、理论计算、材料测试、论文润色、仪器选型分析和销售、科研 AI 等科研服务，与国内外100余家顶尖院校、学术期刊、知名学会、投资机构建立深入合作关系，产学研投融合创新服务的运维模式，助力科技信息的无障碍传播，加速信息的整合利用，推动科技人才在全球范围内的流动及合理化配置。
Okay, good morning, Professor Alexander Matic, and good afternoon to our audience in China. Welcome to eScience Summit Forum. Today, we are delighted to have Professor Alexander Matic from Chalmers University of Technology to deliver a lecture. And before the lecture begins, please allow me to introduce our launched flagship journal, eScience. a Diamond Open Access journal. eScience is founded by Nankai University and aims to publish high-quality academic papers related to energy, electrochemistry, electronics, and the environment. So far, 26 issues have been online with diverse author geography and various research topics. eScience has been indexed by SCIE, CAS, Scopus, and DOAJ. The first impact factor is 42.9, and the second one is 36.6. So Professor Matic also contributed a high-quality review to eScience on understanding the electrochemical mechanics of lithium metal anodes. And I hope everyone can pay more attention to this wonderful review. And thanks to Professor Matic for this contribution. So this year, we also established eScience Energy as a specialized platform for the publication of latest research in energy field. And the first issue of eScience Energy is already online, with the topics including lithium-ion batteries, supercapacitors, MOFs, and solar cells. And we will continue to do our best to build a world-class academic journal in the future. And next, please allow me to introduce our speaker today. Professor Alexander Matic is a professor of physics. Oh, sorry, is a professor of physics, head of the Division for Materials Physics at the Department of Physics at Chalmers University of Technology, Sweden. He's also the director of batteries at Chalmers. His research interests span from fundamentals of soft matter to applied research on materials for energy applications. A particular focus is materials for next generation batteries, for example, non-structured carbon materials, metal electrodes, solid-state batteries, and highly concentrated electrolytes. He also has a strong interest in the use and development of large-scale facilities for synchrotron X-ray and neutron scattering. So today, Professor Matic is going to talk about looking into lithium metal batteries from fundamental processes to operando imaging. So next, let's warmly welcome Professor Matic to give the lecture. And the time is yours, Professor Matic. And I will stop the sharing. Okay. So please, thank you.
So thank you very much, Professor Wang, for the warm introduction and also for the invitation to give this seminar to a big audience interested in energy applications and, of course, in batteries. So what I would like to introduce to you today is about lithium metal batteries. So one of the next after the success of lithium-ion batteries. So we know how successful batteries are today. I mean, they are basically everywhere. Every day we carry around many batteries with us in smartwatches, mobile phones, laptops, but we also use them at home in power tools. They also today we have a lot of electric vehicles, buses, and of course they're coming to grid energy storage. And all of this is thanks to the fantastic inventions that also got the Nobel Prize for the lithium-ion battery, and following the commercialization by Sony in 1991. And we have actually come a long way up to the left there. You see the prototype from Sony, and also the first product where lithium-ion batteries were used was a video camera recorder. And since then, the batteries have become super advanced, but actually we still rely very much on the same technology, with on the anode side having the graphite intercalation material, and on the cathode side we use the transition metal oxides and a liquid electrolyte in between, relying on organic solvents. So while this has been super successful, also for the future, there is an ever-increasing demand on energy content of the batteries, power, life length, safety, cost, and of course, also today, very important for us is sustainability. And all this is necessary if we really want to go to this large-scale usage in, for instance, grid energy storage, in transportation, and is also proposed, for instance, here. You have also the use of electric airplanes. And if one looks, there are many roadmaps in the world on how batteries will develop for the future. So I took this one from the big European project, the Battery 2030 Plus, where we see, of course, the lithium-ion batteries that we use today, which is the core technology, and they have kind of a limit in energy density, both the gravimetric and volumetric, which is built into the types of materials we use. And we see that for the sulfur, for instance, for the future, we have lithium sulfur batteries, which might be very promising for high gravimetric energy densities, so energy content per weight. But we have also, for instance, here solid state batteries with a high also energy density per weight, but also per volume. And there are also more other types of batteries we can consider based on other types of ions, calcium, zinc, magnesium, and of course we have the sodium-ion batteries, which are already starting to be commercialized. So if we look at many of the future technologies, like solid-state batteries here to the right, or lithium sulfur in the center, or using other type of active ions like potassium, zinc, calcium, or aluminum, we realize that a lot of these actually rely on the use of metal anodes and not on the use of intercalation materials like in the lithium-ion battery. So for instance, for lithium sulfur, where you react lithium with sulfur, and you have a very high energy density. Here it is important to match the high energy content of the cathode also with the high energy anode, and then the ultimate choice would be the metal anode. Similarly, for solid-state batteries here, if you really want to exploit the big advantages of solid-state batteries, you should also there use a metal electrode. And of course, if we just look at the numbers, the theoretical capacity of, for instance, lithium metal is almost 10 times that of graphite. So we would directly, by replacing graphite by lithium, we would gain a lot in energy per weight. This is nothing new to use lithium metal anodes. In fact, this was where everything started. And here are some early papers, for instance, by Peled and Auerbach on the use of metal anodes and investigating the fundamental processes. So since the birth of lithium batteries, there has been research, but somehow we have not managed to solve the issue, because as you know, lithium is super reactive, which causes problems when you want to apply it directly in a battery as metallic lithium. Also, from a Swedish perspective, we have an interest to work with lithium, because actually lithium was discovered by this researcher here, Johan August Arvidsson, in 1817. He was working together with Berzelius, and he discovered a mineral. And when he analyzed this, he realized that there is actually a new element as part of this mineral. So they call this new element lithios, from the word of stone, and then there came the name lithium. So coming from Sweden, we have also to work on lithium. So metal electrodes, what is the problem? I mean, if you look at it first, it looks very simple, because the battery configuration could look something to the left. You would have a cathode, some kind of metal oxide. We have the electrode, and then we have some lithium, for instance, on a copper current collector. So we just replace graphite by lithium. However, if you look at the cycling of a typical lithium electrode, what you see is something similar to what you have on the right. First of all, you will actually have a large volume change when you cycle here, because you're not intercalating, but you're actually plating on top of your electrode. The second thing is that to actually plate homogeneously turns out to be very, very difficult. So instead of having a dense bulk phase, what we often end up with is a very rough surface, and also a surface which has reacted with the electrolyte, forming a passivation layer, the SEI. But also this passivation layer can actually isolate part of the metal and causing the formation of so-called dead lithium. Also, in the worst case, we can get protrusions of metal growing through our cell, growing through the separator, so-called dendrites, in the end causing short circuits. And having this in mind, we also have to realize that when using a metal electrode, we need really to have an ultra-high Coulombic efficiency. So to the right, you see just if we have the 1-to-1 ratio between anode and cathode capacity, you can see here that having a Coulombic efficiency of 99.9 is actually not enough, because you will already lose a lot of capacity just after a few hundreds of cycles. So the processes of the metal anodes really need to be reversible to the level of something like 99.999%, which is also very challenging. And here is just to demonstrate how things look. So up here is an SEM image, how typical it can look after deposition of lithium metal on a substrate. So you see it's not a very dense bulk phase. Instead, it's very porous. It looks like a mossy structure. And of course, this is not what we would like to have. On the bottom, you see something which looks pretty, but actually it's not very useful when it comes to a battery. And here we're depositing instead potassium. So this is potassium deposition. And you can see that when you deposit potassium electrochemically, if you are not careful, you get really this kind of dendritic growth with a very porous structure. It looks almost like a forest. It's a beautiful image. But of course, you would immediately have a short circuit in your cell if this was the situation. So these are the challenges we are facing when using metal anodes. So when it comes to looking at this, so one asks the question, people have been working with lithium metal anodes for more than 30 years. So why is it so difficult? So what we have up here is that we somehow need to take a lithium ion from solution, and then we have to deposit it, pick up an electron, deposit it on the surface. But then also to form a dense structure, you need a very efficient electrocrystallization process where the ion finds immediately the right place. So some colleagues, they told me that this is like playing this old video game Tetris at very high speed. And anybody who has tried that knows that in the end, also in Tetris, you form very porous structures. So this is a little bit how metal anodes actually work. So if we now consider the processes that we have to take into account, it's actually a very complex situation we have. We start from an ion in solution here, surrounded by solvent molecules, a solvated lithium ion, which goes towards the surface during charge of the cell. So when you want to deposit lithium, it picks up an electron. So we have to have a desolvation step. First, we have mass transfer in the electrolyte, desolvation step, and then we normally have an SEI. So we have mass transfer to the SEI. And then, of course, you reach the surface, and somehow you need then to find other lithium atoms to crystallize in a dense structure. And the processes, if you look from an electrochemical point of view, this is how it looks if you now do a constant current experiment. Typically, the voltage curve initially drops fast below 0 volt with respect, in this case, we are depositing potassium. You have a nucleation region, which is then signified by a peak. So you need a little bit of a driving voltage to initiate nucleation on a surface, and we'll come back to that. But before that, actually, what you're doing as soon as you start to pass a current through your cell is that you always break down a little bit of your liquid electrolyte. So you are forming this SEI layer, the passivation layer, and it's below this that you actually then start to nucleate. And once you nucleated, you can start to grow. And if you look at these processes, the SEI layer is very important, but also normally you actually have a native oxide layer also on top of your bulk metal electrode, which you need to take into account. And this we showed in this work where we compared the bulk potassium electrode to an electrochemically deposited electrode. So the electrochemically deposited does not have a oxide layer. And then we can see that the over voltage was much smaller. So a few years ago, we started to work on this topic, and especially I want to mention my colleague Shizao Shong. So he was postdoc here at Chalmers, and then later also researcher before returning to China for a faculty position, I think at Kunming University. So he was driving work to really understand the fundamental processes and how different parameters influence the lithium deposition. So together with other colleagues, he used phased field modeling, where you solve the transport equations and the electrochemical equations and then look how different structures are formed depending on how your substrate looked. So we could then follow, depending on different conditions, how what actually influenced lithium deposition. And what came out of this work was that the first thing is for this initial nucleation step, which is very important for the final morphology, is that the radius, the size of the objects that are formed initially when you start a position is very closely related to this nucleation over potential. So the value of this peak in the voltage curve. And we could show them that this nucleation over potential and the critical radius, they were really always correlated. And actually that the size of the initial objects is quite big. I think that the simulations overestimates the size a little bit, but still you are of the order of somewhere between a few hundreds nanometers to up to almost a micron. And you can see actually here in this SEM image of deposited lithium onto a copper surface. And you see that the small crystallites formed in the beginning here, they are of the order of half a micron or similar. So in simulations, you can actually vary the conditions as much as you like. So here's one of the results that we obtained where we could vary either current density or salt concentration. So here we went from really low currents, so 0.5 milliamps per square centimeter, but to super high currents of 20 milliamps per square centimeter, something that you might not achieve in reality. And we could see that when you increase the current, you really also enhance the formation of a very heterogeneous and porous morphology. So the image here below is how the morphology of deposition would look on a surface. And the surface here consists of micrometer-sized protrusions. And then you can see that where you have a protrusion, you actually enhance the deposition, which means that in the end you form a very heterogeneous structure. Similarly, we could look at what happens with temperature, or with, here in the case of salt concentration in the electrolyte, where a highly concentrated electrolyte was proven to be very beneficial for forming a smooth lithium layer. And the key here is actually that what happens in a cell when you run, for instance, a large current or low temperature, basically when you have a transport limitation in a system, is that you get a depletion of lithium ions close to the surface. And if you have a depletion, then you will have preferential deposition on any protrusion that is formed. This is also why high salt concentration is beneficial for homogeneous deposition. So we were looking a little bit in here together on different strategies to stabilize metal anodes to form a very nice and dense lithium deposition. And basically, you have three choices here. The simplest one is, of course, you just modify your electrolyte formulation. As shown in previous slides and from the theoretical work, it should be good to go, for instance, to highly concentrated electrolytes. You could also think about protecting the surface. So basically adding a layer which could steer deposition, so using some kind of functional interlayers. The most advanced is, of course, that you could engineer the lithium itself. So here is an example also of the work of Shizao Xiong, where he and colleagues, they used cerium doping to modify the surface of the lithium anode and promote the growth of certain crystalline directions which are not forming dendrites in the end. Of course, this is super elegant, but also very difficult to do on a large scale. And the most simple is, of course, to just modify the electrolyte formulation. So I'll show you an example of this here. So we worked with several different approaches, for instance, highly concentrated electrolytes, ionic liquids, or also diluted highly concentrated electrolytes. And as shown in the previous theoretical work, if you increase the salt concentration, you should also form a much smoother and more dense lithium metal upon electrodeposition. So we investigated this, actually both theoretical and experimental, and here are the experimental results. So we used the solvent tetraglime and doped it with a lithium salt. And in this system, you can actually very dilute concentrations of the lithium salt to very high. So you can even go here, in this case, you have one lithium per tetragram molecule. So very high concentration of lithium salt here. And what happens in that situation is actually that tetraglime wraps around lithium and forms a kind of effective cation. And then the anion here, TFSI, is completely decoupled. One can look from the electrochemistry that when you have a low salt concentration, you see the overpotential in a symmetric lithium cell increases very rapidly. So you have formation of a very resistive interface. Increasing the salt concentration, the overpotential decreases and becomes in the end very stable. And if we compare to the right the SEM images of the different of the surfaces of electrodes retrieved from cycled cells, you can see that going from low concentrations, it's a very inhomogeneous deposition, and at high concentrations, it's actually very, very smooth. And then comparing to phase field modeling results, you can see again here that there is a match, that at low concentration, you actually form this kind of whisker-like, dendrite-like structures, and that at high concentration, you obtain a much more dense deposition. I also just want to highlight very recent work here from student Chuan Wu here at Chalmers, who actually then comes also from Nankai University, where she has been working on ionic liquid electrolytes together with lithium additives, and where the idea is to actually tune the solvation shell of the lithium to promote a much better deposition. So the paper is coming out soon, and then you can read all the details. But I just want to share with you that her new electrolyte formulation here, you get extremely stable cycling with good capacity. This is in a LFP lithium metal cell, but it's a lithium metal cell with very limited thickness of the lithium electrode. So these are very harsh conditions. And still the cycling looks very good and with a very high Coulombic efficiency. And you can also see on the SEM image how smooth surface you get. Now, having all this both theoretical and knowledge, it's also important to understand how we can investigate metal deposition. And there are also, of course, several things we need to understand. Of course, we need to understand the electrochemistry and electrochemical properties. What we need to do is somehow experimentally to follow SEI formation to get some insight in the nature of the SEI. After that comes the nucleation, and in the end, the growth of the metal structures and the formation of the final morphology. So in our work, we have been using X-ray and neutrons at large-scale research facilities. So for X-rays, the synchrotron sources, where we have mainly been using the Swiss Light Source at Paul Scherrer Institute in Switzerland and the European Synchrotron Radiation Facility in Grenoble. And for neutrons, we have been using the Institut Langevin in Grenoble, which is just close to the synchrotron radiation facility. And the techniques we are using here is that we actually can look at the morphology inside working batteries with different experimental approaches. So starting down to the right, I will show you an example where we used neutron reflectometry to follow the formation of the SEI and compare the situation in a highly concentrated electrolyte and in a standard electrolyte. Similarly, we can study the interface formation with grazing incidence, small and wide-angle X-ray scattering, where we also just probe the really thin layers, just a few nanometers on the surface of a metal when you then drive an electrochemical potential over the cell. And then with X-ray micro and nanotomography, we can actually study the morphology of deposited metal, and this we can also do then in real time. So starting from the SEI, neutron reflectometry is a really powerful tool because you can very precisely obtain information on surfaces formed on your metal. So here we constructed a cell where we deposited a thin layer. It looks thick here, but it's just you see here, it's just some 50 nanometers of copper on top of a silicon crystal, which is used as the substrate here. So the neutron beam comes in through the silicon crystal, and then we can measure what is formed on top of the copper. And this was a dedicated electrochemical cell, so we can change the potential and in this way form the SCI. So doing this, what you obtain is a reflectivity curve with these interface fringes, and these fringes reflect that you actually have some well-defined layers, so the copper and then the SCI formed on top. And what you're looking for is small changes in these reflectivity curves. So you basically you develop a slab model here where you say, okay, which layers do I have? I have a titanium adhesion layer. I have my copper layer. There is always some oxide, and then we have the SCI formed on from the electrolyte. And by modeling these different layers to fit the reflectivity curve, you can then obtain information. And here we could see, for instance, that comparing a highly concentrated electrolyte and an electrolyte with low concentration, we could see that actually for a highly concentrated electrolyte, the SCI is much thinner. It's also less rough. And also we could see that it contains much more inorganic species. So this is a very good method for directly following this. Unfortunately, this method is not, at least not in the present form that we have been working with it. It's not suitable for doing real-time measurements operando. So this we instead are looking into doing with synchrotrons, and this is a project led by postdoc here, Jan Jamros, together with colleagues at the European Synchrotron Radiation Facility in the Battery Pilot Hub. And what we do here is we have an X-ray beam which goes with grazing incidence, so it just touches the surface, and in this way we can pick up very small, very thin layers formed on top of a metal surface. And together with colleagues at ESRF, we have developed this operando cell, so we can actually do measurements and look at SCI formation in real time. So here is one of the results. Also, this is work in progress, which we hope to report to you in detail during the coming months. But what we do here is that we do a CV, a potential sweep, where we, in the electrochemical cell, we are now looking at a copper surface, single crystal copper surface, and we are doing the CV, so we are breaking down the electrolyte, and as we're doing this, we are recording diffraction patterns in this case, and as the electrochemical process goes on, you can see here how we continuously, for instance, start to form lithium fluoride. So we can follow in real time the formation of these breakdown products from the electrolyte. We also have some indications of formation of an amorphous background, and this is then, as I say, work in progress to start to understand this. So this type of operando measurements are really important, and also if you think about how we are treated, if there's something wrong with us, we go to the doctor. What does the doctor do? Doctor actually uses also X-rays to look into us. And what you want to do is to really use the type of operando measurements where you look in real time what is happening and not taking out a sample. So similarly, we can put the whole battery into the X-ray machine and do X-ray imaging. And either you can use this type of phase contrast imaging, which is very similar to what you do when you actually go to the doctor. So you create a real image based on the absorption of X-rays by the sample. And here is one example of a graphite electrode, which we studied, and we looked at how it degraded by lithium plating at harsh conditions. But actually, you can also create images with X-rays by using scattering contrast. So for instance, using small angle or wide angle X-ray scattering, you can select a part of the diffraction pattern and then create an image. So here is an example where we looked at a hard carbon anode and the sodiation of this, and we looked at a scattering signal. But now I want to show you a little bit on the work we did with X-ray tomography. And here we created a micro battery. So the dimensions you can see here, the cell is a few centimeters long, but actually the inner part is only 1 to 2 millimeters. And this is a very simple setup that we started with, where we looked at we just used a lithium counter electrode and then a copper rod as the working electrode. So we were depositing lithium on this copper rod. And the first experiment we did at the Swiss Light Source. So this was Matthew Sad, who was a PhD student at that time, and then together with Shizao. We were working on understanding this and seeing, can we actually observe the deposition of lithium? And it turns out that with the excellent instruments they have at the Swiss Light Source, we could obtain a full 3D image of this battery within 50 seconds with a roughly 1 micro resolution. And what you see here to the right is actually the morphology of deposited lithium over the whole electrode. And this is how a slice looks. So if you take a vertical cut through the cell, this is what we observed then, that we could see lithium structures formed. And in some places, you can see these very large dendritic type of structures formed when lithium is just growing, and you get enhanced growth at some protrusion. So here's how actually an operando experiment looks. So you see down to the left where we have the voltage profile. So we start our deposition, we have the nucleation peak, and then we start to take images when the growth proceeds. And then we switch the current and we do the stripping experiment. So in the beginning, we don't observe anything because the deposition is very close to the surface. We cannot resolve this, but after a while, we clearly see the growth of lithium on top of the copper. And in the end, after plating, so the bottom image here, you can see very tall structures, even up to 60 micrometers formed in this case. When you reverse the current and you start to strip, you can actually see, for instance, if you concentrate on this structure in the yellow circle, how it progressively decreases. So this is successful stripping, also this structure to the left. However, here you can see that this part you don't obtain full stripping, so the process is not fully reversible. So here we have actually the formation of that lithium. So you can, having a 3D image, you can now isolate all the pixels containing lithium, and you can go into detail and study it. So here are 3D renderings of the deposition. So you see in the start, we have quite sparse deposition just in a few locations. And then when the deposition progresses, we get more and more dense. And then you have the stripping occurring here. If you now follow the volume of deposited lithium, you can see that as expected increases almost linearly, which you expect for a constant current experiment. But then when you reverse the current, you have the stripping, the volume decreases. But after full stripping, you can see that you still have some lithium left. So this is your formation of that lithium. Doing a second cycle, you again have the increase in volume and then the decrease. But the second cycle, then the deposition on the already formed surface is in this case much more reversible. What we have here is we could actually also go in and we could look at the formation of some structures. So in this case, we are following the formation of this very tall structure and seeing how it grows up from the surface, becomes thicker, and in the end, it merges also with growth from other parts of the electrode. and forms a very big needle like structures. But in this experiment, we actually cannot resolve the fine details of the structures growing, because we're limited to this resolution of some around 1 micron. So instead, we started to work together with the SRF and in the battery hub at ID16B beamline, where we can obtain down to some 50 nanometer spatial resolution. We don't, in our experiment with our micro battery, we don't really get 50 nanometer. We are more like 150, but still, it allows us to really resolve much more details. So here, the measurements is a little bit slower. If we don't use the best contrast mode, we can do it in 1 minute. So it's a kind of quasi-operando experiment. But for the images where we really want the highest resolution and highest contrast, it takes 8 minutes. So this is more a type of an in situ experiment. What you sacrifice is, of course, the field of view. So you see here that with the nanotomography, we only measure this part, whereas the purple part is what you would measure in a microtomography experiment. But still, we can now follow, and here is we follow the position at 6, 12, 24, and 60 minutes. And this is under review, this paper. So it's available on arXiv. But now you can see that we can, in much more detail, actually resolve the structures here in the deposited lithium. And we can start to understand growth mode. So if we look here, for instance, we have at 6 minutes, we're just depositing lithium in a few places on the electrodes. And it's from these places that you then start to grow, and the growth continues further and further into 16 minutes. And it's really preferential growth from these structures. So what we do now is that we take the electrode and we just flip it. So we look at the electrode from the backside, and the red points here, they mark where the lithium structures actually touches the bulk electrode. And when we now start to grow, after 12 minutes, you see that the number of points where the growth of lithium actually comes from the surface does not increase. So even after 60 minutes, we just have a few points which are in contact with the bulk electrode, which is the points of growth. Once we have one of these very detailed images, we can actually go in and start to isolate what kind of structures do we have. And we basically isolated two types of structures, needle-like and sheet-like structures. And you can see that the needle-like are very thin, whereas the sheet-like are more like a big sheet or something. And if you look at the thickness of the structures, they are all in the micrometer range. And we also compared this to electrodes retrieved from coin cells, where we could find, for instance, again, needle-like structures or sheet-like structures in the deposit. So it's not only in our operando tomography cell that we see this, but it's also in electron microscopy. And what is interesting is that the structures formed do actually not increase in thickness. So we analyze the thickness of all the structures formed in the volume, and you can see here that already after 12 minutes of deposition, you have structures which are somewhere between 1 and 2 microns in thickness on average, and this average stays the same throughout deposition. So this shows that the structures will grow in size, but not actually in thickness. So we selected one small piece here, and we could follow the development of this piece. So here is after 6 minutes, you have the first formation, and then you see how this structure then grows. This is after 12 minutes. And then you have a branch here and the second branch going, and then in the end you also form a sheet. But what you can notice is that it is not only tip growth. the structures actually grow everywhere. So you see that this base has actually increased here in size. So the structures grow both at the tips, at the ends, but also from the root. So I think this methodology is very important, that you can in the end start to distinguish between different types of growth modes. Do we have tip growth, which maybe depends a lot on is a result of depletion, for instance, in the structure, or do you have base growth in this case, and how and what the kinetics are. So just as an outlook for the future, what we are also working on now is to develop this method to go to more realistic conditions. So we are developing a cell here where we can use separator and also apply pressure. And here is some very preliminary results on lithium-lithium deposition under pressure. And also here is another example below where we look at the solid state battery, where we look at the interface between lithium and solid state batteries. So with these examples, both from the theory simulations and then also experimental characterization, I hope I've shown you a path towards understanding metal deposition, and then that we in the future can obtain safe and reliable lithium metal batteries, and that this relies on understanding what goes on the atomic level and being able to follow the processes in real time. So with this, I just like to thank all the co-workers and really highlight the work of Shizao Xiong and Youssef Rizel and Matthew Sad on the imaging part, and also all the collaborators and funding agencies. And thank you for your attention.
Okay, thank you, Professor Matic, for the wonderful lecture. And actually, there are quite a lot of audience from different online live streaming platforms, and the audience are very active to ask questions. And our colleague, I think, have selected several questions and pasted in the chatting place. So the first question is about in the context of operando imaging techniques for lithium metal batteries, what are the key differences in spatial resolution, time resolution, and applicable battery systems between different imaging methods? For example, operando TM, X-ray computated tomography, and in situ optical microscopy. So Professor Matic, and yeah, you can also read the question from the chat room.
Yeah, no, so I think that's a good question, and starting from optical microscopy, obviously the resolution is quite limited, and also it's very difficult to get a full 3D image because the visible light cannot penetrate the structures, and also it's difficult to have a realistic cell in that case because you need a casing where the light can penetrate. Electron microscopy can give you super high resolution. The problem there is to have a reasonably large field of view and to have a realistic cell configuration. This is where I think that actually the X-ray tomography is at present the best technique, because we can have cells where we can have similar conditions as we would have in a real battery. And we can also run them in real time. So we can also actually use relevant current densities and similar. And with X-rays now, we can achieve a time resolution which is below 1 minute. I think we can go even faster. And if you sacrifice resolution, you can actually also, there are very many nice examples in literature where people also use a real commercial cell. Then, of course, you cannot look at all the fine details, but you can still get a lot of information, for instance, on delamination of electrodes or defects forming and so on.
Yeah, okay. Thank you for the detailed answer. And the second question is, I think it's quite general question, how to select the appropriate operando imaging technique for studying specific fundamental processes.
Yeah, I think that is a very open question. But as
Yeah.
always, you have to define what is the length scale and what is the time scale that your process occurs on, and then try to find a matching technique. So, for instance, in our case, we can really follow the growth of lithium structures because we have the resolution there of even down to maybe 150 to 100 nanometers and a reasonable time resolution. But at the moment, we have a little bit trouble to capture, for instance, nucleation. So nucleation occurs very fast. So you need something where we can be really precise and capture a process that occurs probably in a few seconds. And also to have a very high resolution, probably we would need to push the resolution maybe down to 50 nanometers to be able to see this. So understanding actually what is your problem, what is the time scale and length scale, this will then guide you to the right imaging technique.
Yeah, sure. Okay. Thank you. And the third question is, what are the current limitations of operando imaging techniques in studying lithium metal batteries? For example, equipment cost, sample preparation complexity, and interference with battery normal operation.
Yeah, so that's a good question. Of course, you need access to a synchrotron. So if you don't have that, then it's difficult. You can do something
Okay.
also on lab instruments, but that is it doesn't give you the operando capability. I think otherwise the biggest limitation is to develop a cell which represent a realistic battery, and you also have that the very intense X-rays might interfere with the electrochemistry. So we know that if we put on the full flux that we have of X-rays, we will actually destroy the cell. So we are always limiting the number of photons going to the cell. So this is always a trade-off. If we have more photons, we get a better image, but we destroy the cell. So I think this is the biggest limit, to understand how to perform the measurement with high quality, but with a limited flux, and also to develop very good operando cells that mimic a real battery.
Mm-hmm. Okay. So maybe I will take the chance to ask the last question. So you already have collected many unique images for the batteries. Is it possible to combine this data with like AI techniques to predict best performance batteries in the future? Because I know that for this machine learning or these AI tools, it is very easy to use the image data.
Yeah, so this
So
is
I
I
want
think
to hear your opinion.
that I think that is a very promising direction, and we have just started to do a few small things, not very much, but I know that there are other groups working on this in other laboratories, and of course when we look at our data. We do a lot of manual work, so and there I think an AI method that could look at all the details and maybe also calculate parameters, provide statistical information on the structures would be very valuable. And this I am sure that this will be an important direction for the future. It will also enable, I think AI will enable us, and machine learning, to much faster get images or interpreted images from the experiment, so that when we do our experiment, we already after a few minutes maybe have information that can help us decide what the next step in the experiment should be. So I think this is super promising.
Yeah, okay. So due to the time limitation, so we have to conclude the lecture today. And thank you very much for giving us this wonderful talk and also the inspiring discussions. And thank the audience online for listening this lecture. And I wish you all have a very nice new year. And I hope you can have the chance to visit Nankai in the future in person. So
Yeah.
have a good day. Yeah. See you
Thank you,
next time.
everybody.
Bye-bye.
Thank you. Bye.
Bye.
好啦，王老师，那咱们这次会就圆满结束了。
哎，好的，好，谢谢大家啊。那
谢
我就退出了。
谢王老师。
穿越时空的科研之云，拥抱科技进步的脉动，在科研的广阔天空中，每一颗星辰都闪耀着探索真理的光芒。科研云自2020年3月创办至今，目前已发展成为中国最大的科研科技传播平台，旨在为学术和产业界一线科研人员提供一个了解和交流国际前沿科技的新途径。希望能以最便捷高效的方式，密切连接平台订阅用户与学术界、产业界的专家学者，一起交流国际学术和产业界的研究进展，促进学科交叉和产学研互动衔接，引爆思维火花的碰撞。基于科研云科技学术平台的品牌优势，萃取海量学术视频信息，打造新型科技数据库和专家数据库，并承接国内国际品牌学术会议的宣传、直播、承办等业务，服务于政府的科技规划和政策实施，高科技企业的科技成果转化和技术咨询，高等院校和研究所的人才招聘和学科建设评估等项目。打造一站式科研服务平台，包括科研耗材、科研绘图、理论计算、材料测试、论文润色、仪器选型分析和销售、科研 AI 等科研服务，与国内外100余家顶尖院校、学术期刊、知名学会、投资机构建立深入合作关系。产学研投融合创新服务的运维模式，助力科技信息的无障碍传播，加速信息的整合利用，推动科技人才在全球范围内的流动及合理化配置，促进学科交叉和产学研互动。未来科研云致力于打造科研传播第一品牌。穿越时空的科研之云，拥抱科技进步的脉动，在科研的广阔天空中，每一颗星辰都闪耀着探索真理的光芒。科研云自2020年3月创办至今，目前已发展成为中国最大的科研科技传播平台，旨在为学术和产业界一线科研人员提供一个了解和交流国际前沿科技的新途径。希望能以最便捷高效的方式，密切连接平台订阅用户。高效的方式，密切连接平台订阅。